take a quick look at 617. I'm going to look at one of the structural members, either AC or AD, to determine the magnitude of the stress in that structural member. So I'm going to come over to the document camera, and I will need somebody to run the calculator for me because I didn't bring one today. All right, so these are the values that the students got, and I'm just going to draw a really quick representation. This is AC, and this is AD. All right, so let's take a look. The first thing that we need to do is to find the reaction at A, which is purely in the y direction. And we'll have a reaction at B in the y direction, and reaction at B in the x direction when we do our statics. We have 150 kilonewtons pushing down, and here at the bottom at C, we have a 75 kilonewton load pulling to the left. All right, so the first thing we do is our statics on the entire structure. Summation forces y equals 0, summation forces x equals 0. And in the y direction, we have RAY, RAB, and 150, sum to 0. But we don't have symmetry because of that 75 kilonewton force. Here we have, in the x direction, negative 75 kilonewtons plus RBX equals 0. So that's RBX is equal to 75. So how are we going to find RAY? The easiest way would be to sum moments about point B. And so we can say negative RAY times 10 meters. Then this 75 would be counterclockwise. 75 kilonewtons times here we'll use the horizontal distance, which is, excuse me, the vertical distance, which is 2 meters. And then the 150 is also positive. And since that's a vertical force, we use a horizontal distance of 5 meters. And we can solve for RAY this way. So this is 150, and this is 750. They're both positive, equals RAY times 10, or divided by 10. So I get that RAY is 900 divided by 10, or 90 kilonewtons. Is that what you got?
Yep.
Yeah. Excellent. All right. So that's the good news. Somebody always, whoever's here, I think it's Dr. Cuddy, likes to use really small little screen. So I always have to forget, I always forget to widen it out. All right. So if we continue with that, let's look at A. And so here at joint A, we have RAY, which is 90 kilonewtons, pushing up. And we have AD, and we have AC. All right, so first of all, since this is pushing up, at least one of these is pushing down, right? And also, since one of these then, if it pushes down, will be pushing to the left, the other has to push to the right. So let's just do AD this way and AC this way. All right, if you did it the other way, it would come out in the math. But now let's look at the summation of forces X into that joint A equals 0. So we have AD in the x direction, which is positive, minus AC in the x direction equals 0. Are those two equal each other? In the y direction, we have positive 90 plus AD in the y direction minus AC in the y direction equals 0. So those are our basic equations. Hang on. All right. So which one would you like me to solve for? Do you have a preference, AD or AC? Okay. So let's go. It really doesn't, but we'll be so close to finding the other one. So let's look at the geometry of AC. This height from A to C is 2 meters, and this distance is 5 meters. And for AD, this height is 4 meters, and the distance is 5 meters. So we construct our physical triangles. So then in the x direction, Okay, so here's something else. I don't know if I want to introduce this to you right now or not. There's a shortcut to this, but let's not do it. Let's just find this angle. Let's just call this the angle for AC. We have opposite over adjacent, which is tangent, 2/5. And for the angle at AD, we also have opposite over adjacent, only our numbers are 4/5. So what are those two angles? What's the angle at AC? Say it again.
21.8.
Thank you. And how about the angle at AD? Inverse tangent 4/5? 38.6 degrees. Thank you. All right. So to do summation of forces in the x direction, AD in the x direction, we're talking about the cosine of that angle. So it's AD times the cosine. Oh, sorry. I should put this over here just to be less confusing. AD, I guess I'm just, I don't know. It's less confusing, not really. Okay, AD in the x direction is AD times the cosine of 38.6 degrees. Subtract from that AC, oops, help if I did that, there we go. AC in the x direction, which is AC times the cosine of 21.8 degrees equals 0. Let's just solve for AD. That equals AC times the quantity, cosine 21.8 over cosine 38.6. And those are both in degrees. All right, now if we have AD, we could substitute it here. Do you have a value for this? What is the value of the cosine of 21.8 degrees over the cosine of 38.6 degrees?
1.19.
There we go. Super. All right, so if we substitute that in when we do our summation forces in the y direction, we have 90 kilonewtons plus AD in the y direction, which is 1.19 AC. Now, if we look at AD in the y direction, it's going to be times the sine of 38.6 degrees minus AC in the y direction, which is AC times the sine of 21.8 degrees equals 0. And so we could solve for AC. We'll put 90 over here. We'll bring our AC stuff over to the left-hand side of the equation. So we have AC factored out times the sine of 21.8 minus 1.19 times the sine of 38.6, right? So you can find a quantity for this, and so 90 over this parenthetical is equal to the value of AC. See, it doesn't look like that's going to be a huge value to me. Maybe it is. Maybe this is tiny. Looks to me like it's going to be negative, actually. Oh. Yeah, Jess, you're usually my go-to guy on that, but that's okay. Say it again.
0.359.
0.359? Positive?
Yeah.
Okay. And so if you take 90 and divide it by 0.359, what do you get? 250? And that's very close, isn't it? And it's in compression. So that is correct.
You got what?
He said 250. So 241, yeah. Sorry?
In compression?
Yes. If you look at the picture, the original picture that I drew, if the signs came out properly, AC is pushing on the joint. So that's compression.
That's how you assign compression. The member itself.
You look at the, when you cut the member, you check to see if the member is pushing on the joint or pulling on the joint. So in other words, once you do the analysis at the joint, you look at that structural member as being a force acting on the joint. And if it's pushing on the joint, it's compression, and if it's pulling on the joint, it's tension.
I misunderstood. I thought you looked at it from the see which way your forces are coming out.
No, no, but it is compression, by the way, I have it drawn.
So I did it backwards.
Okay,
Mine is
right.
compression.
Okay, well, AC is in compression, is that what you're saying?
Yeah, but based on what I thought it was
Different?
different.
Okay, right. Now, if you do, you may be getting mixed up if you did the method of sections in statics, because when you do the method of sections in statics, it looks a little bit more like what you're describing. It's exactly the same idea, but it looks a little bit more like that. But what we're really looking at is just this joint, and anything that's affecting the joint, we view as being like it's not exactly a force, but it's a structural member bearing a force. And so is that force pushing on the joint, or is it pulling on the joint?
So when you do AC, the other side of AC, it'll also be compression, but it'll be
Yeah.
compression on C
Yes, exactly.
of the same
That is
magnitude.
exactly correct. Because otherwise it would move.
Right.
Yeah, super.
So then, can you explain why if we only have 150 kilonewtons down, those forces are so great on those two members?
Well, it just can happen. You just distribute it. Tension, compression are opposite in sign. We also have that 75 kilonewton force. So, you know, you just have it, it's distributed in an odd way. And the 75 really pulls it off, because if you think about it, the 75, A can't bear any of it, can it? I mean, because it's horizontal. So you're going to be putting that somewhere else on that truss.
Well, I did my math right.
It just didn't make sense. Yeah, very good.
Well, then when I saw for BC, I only got 78.
That's, yeah. When you have something like this, and Caleb, it just brings up a very good engineering point that you're bringing up. When you have asymmetrical loading on a truss, it can do very strange things. And so it's like if you build a roof truss, and your roof truss is symmetrically loaded, everything makes sense. But if you do something that puts a load into it that's off kilter, you can just have to beef up that roof like you cannot believe. So anyway, so it's a very good engineering consideration.
So then that 75 would make sense that BC is 78 and those ones are 280.
Exactly, yeah. So what's really happening is if you think about it, joint A can't bear anything in the horizontal direction. So everything is being transferred elsewhere in order to keep that load. And that's sort of this sort of a truss is more or less called a scissors truss. And it's a kind of truss that you would put in for a cathedral ceiling. Except for on the cathedral ceiling, it really is anchored at both points, and then you have to reinforce the heck out of it right here. But what also happens is that if you think about this, if you have this kind of a truss, the house is always trying to go like this or like this. So the only thing, so right here where the wall connects up to the truss or to the roof structure, you also have an incredible load. So you have to reinforce it here so it doesn't splay outward, and you have to reinforce it here so that the walls don't splay outward. So it's a lot. They call it live load. I mean, and it's not really an engineering term. It's more of a construction term. But it really is. It's very. There's a lot of motion in loading something like this. So, excellent point. Yes.
Okay, so it might be a stupid question.
No.
But just so that I can complete this thought.
Sure.
So in order to find AD, you would just take your forces in X.
Right.
And
Absolutely.
that equation, and then plug AC in. So you would have the AD times cosine of
Yep.
38.6 minus 250.
Times the cosine of the other angle.
So
Right.
minus 250 times the cosine of 21.8.
There you go.
Okay.
You got it.
Okay.
Very nice. Yeah.
Sorry, I did my math wrong.
Oh, you did? Was it negative?
It was a negative 0.37.
See, that's weird to me. There's something wrong with that. Because what that means is that I've chosen the direct. Okay, so if it comes out to be a negative, which I kind of looked at that and I thought, because the sine of 38.6 should be greater than, let me put this here. The sine of 38.6 is going to be greater than the sine of 21.8, right? So if you multiply it by 1.19, then this quantity is going to be larger than this quantity, and this is going to be a negative. That made sense. But Thank you for correcting that. So what that means is that this is minus 250
No,
and
242.
242 or something like that. Okay. So what that means then, if we go back to AC, that means that we've chosen this sign incorrectly. That means that it's like this. That means that AC is in tension. Okay? And that means also that AD, don't change it yet, but you'll find out that it's going this way, and so this is going to be in compression. Can you actually see what I just did? Sorry, that would be helpful right there. Okay, yeah.
So when we look at a joint,
Yes.
if a member has a force moving away from that joint,
Yes.
we would say that that member is in
The joint.
tension?
Yes, that is correct because it's pulling on the joint.
Okay.
Yeah. And if it's going down, if it's pushing into the joint, then it's in compression because it's pushing on the joint. Yeah. And you can think about it because if you think about, and we're not doing this, but this expands the thought. If you think about the structural member then instead of the joint, if it's pushing on both sides, yeah, it's going to be in compression. So, yeah. Very good. All right. So, yes?
I think so.
All right, we'll see what happens next, right? Yeah. So we've sort of cut up the first, well, I shouldn't say that. We have sort of cut up the first part of this class, the first part of this chapter. And this concept of normal stress is going to come up over and over again. The next thing that we're going to talk about today is shearing stress. And shearing stress is a little more difficult to handle. So we're going to do something called average shearing stress today. And then later in the semester, we're going to find better values for point value shearing stress. But basically, let's start by drawing something like this. This is sort of like my favorite way to look at shearing stress and normal stress. Okay, if you have say a wooden beam, and anything that's shaped like this is just referred to as a prismatic member. And if you have a glued splice somewhere in that structural member, so you have a plane that it's called oblique, meaning it is not square to the cross section. So in other words, there's some angle between a pure cross section and this glued splice. If you pull on this structural member or push on this structural member without allowing it to move, you're going to have a force and a responsive force, or else it's going to move. What's going to happen on this glued splice, and why do we look at the glued splice? Because that's what we're interested in. This is a very strange part about analysis in mechanics of materials. From an engineering point of view, what we're always getting at is where is this thing going to fail? Where is it going to slip? Where is it going to pull apart? Where is it going to crunch together? So the reason that we look at the glued splice is because that's where our interest is in terms of some sort of a discontinuity. So there's an element of thinking about that first, because you might say, well, why don't we look at the shearing stress or the normal stress on the rest of the member? And the answer is you can. It's just not an interesting place from an engineering point of view. What you're interested in is where it's going to fail. All right. And another case like that would be, let's do something like this. There's a great problem in your textbook where, let's just say that you have a connector that looks like this, okay? And you have some sort of a plate that it's going through, and it's connecting two plates, okay? Well, if you pull on this, there's a couple of different things that can happen. These plates can fail, in which case it's going to fail along this plane, or this bolt can fail, in which case it's going to fail right here. Which one is more interesting? Well, what's more interesting is which one's going to happen first, because once one of them happens, you don't have a structure anymore, right? You don't have a bolt, you don't have plates, you don't have anything connected. So before you do any sort of a mechanics of materials problem, The good news is that the math tends to be quite a bit more simple than what you're doing in dynamics. How many of you are in dynamics right now? Okay, and the rest of you have had dynamics maybe? Yeah. So the math in here is quite a bit more simple than dynamics, but you have to kind of take a minute and think about it a little bit. And not that you don't in dynamics, but you have to think about like where it's going to fail. Well, and what causes it to fail? Let me just ask you this question. If you have this bolt and you pull on it, sometimes it would fail here and sometimes it would fail here. What would cause it to fail one way or the other? I mean, by looking at this picture, you don't know, do you? So what would it depend upon, do you think?
Pretty much which is stronger, the plates or the bolts.
Perfect, that's exactly correct. If you put the bolt up here and this is made out of silly putty, it's going to pull right through. If on the other hand you have this made out of tungsten and this made out of silly putty, it's going to pull apart right there. So those are the questions that we start to answer in this class. But here, so that's why we're looking at the glued splice. We are interested in the glued splice. It may be stronger or weaker than the rest of the structural member, but this is the area that we're interested in. So if you think about it, if we apply this type of a load, which is called an axial load, we're going to have two kinds of stress. We're going to have one that tends to pull this apart, which we know to be sigma, and we're also going to have one that tends to slide along that glued splice, which is tau, or a shearing stress. So one of the interesting things about shearing stress is shearing stress tends to concentrate at areas of discontinuity. And this gets into a little bit more analysis that we'll cover up in, I think, chapter 5 or something. So this is the whole, if you have a weak spot, that's where it's going to fail. So anytime that you have something that is unusual or weaker, that's where it's going to fail. The other thing is that sigma tends to be an axial phenomena, meaning that if you have a normal stress or a normal force and you pull on a cross-section, the sigma is only in one direction. But tau, on the other hand, acts over an entire plane. So we refer to it as a planar phenomena. Okay? So when we talk about shearing stress, what we're really talking about is the tendency of a structural member to slide, right? Now, for the couple of you who have had fluid dynamics, this is also a very important phenomenon because shearing stress in a fluid results in a viscosity. How hard it is for a fluid to flow against itself is part of the equation for viscosity. When you're talking about solids, we're just talking about that tendency to slide. So the interesting part is that we know that sigma caused by a load is P over A, and it turns out that tau is mathematically just as simple. It's V over A, which means that V is the component of the force in this direction, and P is the component of the force in this direction. Or we may, in this case, want to call it F because they're not perpendicular to each other. Okay. So sometimes materials fail in shear, and sometimes they fail in normal stress. And one of the things that we have to do as engineers is to determine which one of those failures is going to occur first, because this goes back to the idea of the weakest link, so to speak. Once it fails, you don't really have a structure anymore. So sometimes you'll have to test both. You'll see where it would fail in normal stress and where it would fail in shearing stress. And whatever one fails first is the one where it fails. Yes?
Did you say that V is a force?
Yes, V is a force. It has the same dimensions. So there's force over area. It's just the component of the force. So let me see if we have a really interesting problem. I'm going to assign problem in the textbook. One of your homeworks tonight is going to be 118, which is the problem of a steel rod supported as shown, which is basically the aluminum plate problem. that I just described. So it may fail along the edges of the head of that bolt, or it may fail, it may pull apart. So those are, and it may actually fail in another different place too, but I'll leave that to you to see when you take a look at that problem. All right, so let's take a look. The big deal with finding tau is to find that angular relationship between V and A. Here, V and A are parallel. Here, F and A are perpendicular. Okay? So it's always about this angular relationship. The other reason that I like to draw this is because I want to show you that sigma and tau are always perpendicular to each other, but they are not always in, there's no reason for them to be in the x and y direction. They're just always perpendicular. And then why do we always talk about perpendicular? Why is that such a big deal? Well, if we use x and y, for example, which we've done in Cartesian coordinates for a long time, or if we use sigma and tau in whatever direction they are, if they are perpendicular to each other, we can completely describe the state of stress using tau squared plus sigma squared equals, square root of that is the state of stress. So in other words, almost every structural member that's put into stress can have both a shear and a sigma, or tau and a sigma, but the complete state of stress is at some angular relationship between that. If you remember, if we don't have a perpendicular coordinate system, like if we did some y prime, x prime, and this angle were other than 90 degrees, we would have to describe the resultant vector as being something in the x prime direction, something in the y prime direction, plus 2 times the cosine of the angle between them, times xy, I guess. Okay? And what that does is, in other words, we have to use the law of cosines, which is a little bit more complicated mathematically. So any time that you can keep two vector components of something perpendicular to each other, since the cosine of 90 degrees is 0, you eliminate this term, and so your math becomes much simpler. So that's why kind of as engineers in a practical way, we're very interested in having most of our coordinate systems perpendicular to each other, because it eliminates a lot of the mathematical issues, where there's really no particular physical reason for doing that, but it greatly simplifies the execution of the problems. All right, so let's take a look at problem. I would like to do a very simple sigma tau problem. Let me take a look first of all at, in this textbook, problem 117. Let's see if I can zoom in on this, and then we'll talk about it a little bit, and then I'll work it out. Okay. When a force P, which is an axial load, reaches 1,600 pounds, the wooden specimen shown fails in shear along the surface indicated by the dashed line. Okay, so this makes sense, doesn't it? What it's really saying is this component, whether it's made out of steel or whatever, is stronger than the wood. So when you pull on it, the steel is going to tend to pull through the wood, isn't it? Okay, so what we're really saying is this is the surface that bears a shearing stress, because the shearing stress is directed along this plane, which is in the same direction as the load. Now there are some normal stresses here, but they don't really come into play. In other words, if this were going to fail in normal stress, it might fail right here, right? In other words, where the wood and the steel come together. I'm assuming it's steel. It is. Oh, never mind. I'm not assuming it's steel. All right, it is steel because it says so in the book. But what we would say is if that surface were weaker in normal stress, that's where it would fail. But they're telling you in this problem it's going to fail in shear, it's going to fail along the wood, and it's going to fail along that plane. Okay? So what they're basically telling you is they want you to determine the average shearing stress along that surface at the time of failure. All right, so I'll go ahead and draw this out. And basically, how am I doing on time? Oh, we're doing good. This is I think I can get this problem done in the right amount of time. So we have this type of a metal, I don't know what you would call it, a doohickey perhaps, okay? So, technical term. There we go. And we have a piece of wood that is, I guess we're actually pulling on the wood, aren't we? So let's get rid of this. And we're pulling like that. All right? And so they're telling us that that metal essentially is just going to scrape off this little top piece of wood along this surface. And because P and this surface are parallel, we are talking about a shearing stress. And they ask us to find the average shearing stress, which is just, in this case, P, we've formerly called that V, over A. So we know that our P is 1,600 pounds, and now all we need to do is to do a little bit of analysis to determine what that area is. Okay, well, they tell us that it fails on this line, and that goes back, the wood goes back a certain thickness, doesn't it? So the area is actually this distance, which we're told is 3 inches, times how far it goes back, the thickness, which is 0.6 inches. So here, the area is just 3 inches times 0.6 inches. So we get 1,600 pounds over 6 times 3 is 18 with a decimal point, inches squared. So we have 1,600 pounds over 1.8 inches squared, which is, what, 80 psi or something like that? If I take 1,600 and divide it by 1.8, it'll be like 800, 600, I don't know. Somebody's going to have to tell me.
888.
Thank you. 888 psi. All right. So that means that when we pull on this, we're pulling on it with a continually increasing force. And when we get to 1,600 pounds, it fails in shear along this surface. So we take our failure load, the cross-sectional area on which it failed, and we have the average shearing stress at the time of failure. All right? Any questions? Okay, so let's take a look. I've assigned 118, which is a problem like this. It's similar to this. The other one I'd like to do is 1.20, and those will be your 2 homework problems for, who's going to come Monday? Nobody, I hope? All right, so don't come Monday. This will be for Wednesday of next week. But let's talk a little bit about problem 120, and then we'll, just analytically so that you'll have some information about it. And then we'll also talk about problem 118. All right, so here's problem 120. We have 3 wooden planks fastened together by a series of bolts to form a column. The diameter of each bolt is 12 millimeters, and the inner diameter of each washer right here is 16 millimeters, which is slightly larger than the diameter of the hole in the plank. Determine the smallest allowable outer diameter of the washer, knowing that the average normal stress of the bolt is this, and the bearing stress of the washers and the planks must not exceed 8.5 MPa. It's a very long problem, but what we're basically doing is we're saying it could fail 2 different ways. Okay, the bolt might fail in normal stress. Okay, so if you apply a certain load to it, where the load is going to be in this direction, it's actually going to be like that. But we're clamping it together. So if the bolt fails, it's going to fail on the diameter of the bolt. So it's P over A, the diameter of the bolt. It's a little bit more complicated when we talk about the bearing stress. What we have, if you look at the hole that the bolt makes and the washer around it, if it fails in a bearing stress situation, this is the area that's going to absorb it. It's going to be, whatever is in the center is not going to hold on to that. This isn't really a shearing stress. This is it's a different kind of a normal stress, really. But we're talking about if it fails here, there's just this piece. The bolt is inside, the washer has some outer diameter, and you're basically going to fail on this circle, or this, yeah, it would be a circle with a hole cut out, an annular circle is what it's called. And that's going to be the area which it fails. So they give you a normal stress, 36 MPa, which is 10 to the 6 pascals, Newton per meter squared, equals P over A, right? And so from this equation you can figure both, but the areas are going to be different. So you need to think about that and draw it out, but this is the sort of one of the pictures that you're going to come out with. The other one's just going to be, if the bolt fails, it's just going to be the circle that is the area of the bolt of that particular diameter. So in other words, once you do the analysis, the math is going to be simple. It's just getting to that point first. The other problem, 118, we have a load P, so we're pulling down on this steel rod supported as shown by an aluminum plate. Here's my aluminum plate. We have a 12 millimeter diameter hole drilled into it. The shearing stress must not exceed 180 MPa on the steel rod. This is the rod, this is the plate, and 70 on the plate. Determine the largest load P that can be applied. Okay, so this can fail two different ways. If the aluminum plate fails, it's going to fail right here, isn't it? And if you draw that, it's going to look like a circle because this is circular. It's going to be right here, and it's going to fail around that steel rod.
We can't see the front.
You can't? How's that? Is that better? Do I have everything in the picture? I do. Okay, the other way it could fail is that if the aluminum plate fails. If the steel rod fails, what's going to happen is it's going to pull right through here. And for the steel then, it's still going to be a circle, but this time the circle is going to be 12 millimeters. Okay? And then it gives you the maximum in each. And so what you have to determine is which one will fail at the smallest load. So in other words, you're working this like two problems, but you're finding the smallest load because once it fails, it's gone. And that's where the failure will actually occur. The other one is just a theoretical number at that point. The other one is to tell you that instead of building a plate out of aluminum, you should build it out of titanium, or instead of being the rod out of steel, you built it out of titanium because you need a higher failure stress in the one that did fail. So in other words, this is the weakest link idea once again. A chain is only as strong as its weakest link. Once it breaks, it breaks. It's not a chain anymore. Okay, so do you guys have any questions? All right. Well, gentlemen, come on in. We're done. Have a great long weekend. If you have any questions, don't hesitate to email me over the long weekend. I'll be around. Or on Tuesday of next week. Wednesday we'll come back and we'll just continue our discussion of shearing and normal stress. Have a good weekend.